Okay. Do you guys have, I assume you do, YouTube on your phones?
Yeah.
Can you go to this channel? It should be right there, right now. I probably will change the name of it. U of SC Professor. Just, there should be a live stream going on right now. That should be the channel name, yeah. Could you?
I haven't been able to find the yeah, I couldn't find it either.
Huh. That's okay. Let me send you a link then. I'm going to send you a link through email to all of you. And I just sent it to graduate students. Students, I'm going to send it to undergrads right now. Are you able to? Did you get the email?
Just got it. Yeah, I just got
Did you? It does have a link on it. Can you click on the link or how does it work? There is one participant. Who is this person? No, I just want to make sure that you like online students can join the live stream.
Oh, okay. Yeah, I got to sign into an account.
So it doesn't go straight to the YouTube app. Is what?
yeah, you said live streaming isn't available right now.
So who's online? One person. Is it just a random person?
It says live stream is unavailable.
Okay, I guess we have to. I hate this. Okay. How can I share this? What time is it? 5:25. Oh, okay. I'm gonna send another link. This should work. Could you use this link instead? Okay. Are you able to join? So you just, for those of you who just came into class, please, I sent you an email with a link. Please see if that link works or not. That's the link to the YouTube live stream. If that works, then hopefully we're going to get a better quality online lectures. And we don't need to use Blackboard system anymore because works. Okay, but it has a like 5-second lag, right?
I don't know. Can you like wait a little bit?
Yeah, there's a lag. I'm gonna stream today's lecture on Blackboard anyways as well. Just on Blackboard, yeah. But that is only, again, only for graduate students. Okay. Okay, if you're joining this session on Blackboard, which I see there's one student here, I sent you a link to a YouTube live stream. Hopefully the live stream's quality is better. And all of these will be recorded and will be put on this YouTube channel as the U of SC professor. So later on, you can have I will send a link to the channel as well later on. So you don't need, if you can't find it, you don't really need to worry about it. And I am right now, I'm recording on Blackboard as well. There are 4 participants. Okay, that's good. I'm also recording on Blackboard, but I assume we're gonna stop recording. If everything goes well with the live stream, we are gonna stop recording on Blackboard and we are going to stick to the YouTube live stream. So please, graduate students who have access to both recordings, please check both of those, and let me know which one has a better quality. And if you are joining live, keep in mind that the YouTube live stream has like a 5-second lag, which I think is going to help with the quality somehow. Okay. Is there any questions about the course in general? Right, the materials we cover, the homework, or anything? No. Just keep in mind that your homework is due on Monday. If you are a face-to-face student, you have to make sure that you are. Let me see. You have to make sure that you submit the. Okay, there is one person asking how they should ask questions. It is a live stream, so you can ask questions. There's just some lag, 5 seconds, so you'll get the answer a little like with a 5-second lag. So that shouldn't be a problem. But I see the comments. So if you're in class, you want to join in through the live stream, you're welcome to do so as well. But I assume it's gonna be hard to follow both of the class. Well, both of the class and the live stream together. Okay, where was I? If you are a student of the face-to-face section of the class, you have to submit a hard copy on Monday. If you are a student in the online section of the class for the graduate students, you have to submit it online through the Blackboard portal. And we try to grade everything in less than, yes. What do you mean? Like you want us to print out the homework and like or something? Like type it in and print it out? Is that what your question? Or because if you're bored, yeah, go ahead. No. You don't. Oh, so you're asking about the homework questions, right? You only. No. You don't need to. Only the solutions. Just the work. Yep, exactly. You don't need to. And just submit your solutions. That's the only thing you need to submit. And okay, so that's it for the homework. We are going to finish the discussion on chapter 1 today. We essentially have we are getting a question about whether you need to type the homework. You don't need to type the homework, just submit your solutions. If you want to submit online, just scan your work and submit it on the portal. Okay, we are going to finish the discussion on chapter 1 today. We will solve some example problems. The example problems is essentially your book problems, or your book problems. And I'm going to give you some time. I'm going to give you the problem. I'm going to give you a couple of minutes to think about it. Then you can volunteer to come to the board and we can solve it together, get a bonus point. If there was no volunteers, I will solve the problem myself. And that's it. So let's try to finish the chapter 1. As far as I remember, we started talking about the viscous flow, right? The idea was we have two, from a viscosity standpoint or friction, we are going to have a classification of the flow. that divides different types of flow to two classifications. One is going to be inviscid, and the other one is going to be viscous. Right? We talked about this in detail, and then we talked about the flow over an airfoil using both of these assumptions, inviscid assumption and the viscous flow assumption. We talked about the formation of the boundary layers and what is happening, what happens inside a boundary layer. Why do we have the velocity gradient in a boundary layer? If you don't remember any of these topics, or if you have a question, please ask your questions, but I'm assuming we have talked about this, and I'm going to continue the discussion. We are going to get this type of boundary layer if you include the effects of friction, including friction. Okay, the idea was we have some sort of velocity gradient inside this boundary layer. And since we are including the effects of friction, we are essentially assuming that the shear stress is present at the walls. How do we calculate the shear stress? The shear stress is related to the viscosity of the fluid and the velocity gradient, right? This is the velocity gradient at the wall. Okay. But the velocity boundary layer, or which we usually call the velocity boundary layer just a boundary layer, is not the only layer that will form around an airfoil. If your airfoil or wing or whatever is at, let's say, a temperature TB, and the flow temperature that is approaching this boundary layer is at T infinity, you will have a formation of another type of boundary layer, which you have seen in your heat transfer course, and that is called the thermal boundary layer. Thermal boundary layer. With the thermal boundary layer, the heat flux close to the wall becomes very important. That heat flux close to the wall, we can use the Fourier's law of conduction to analyze. That's the negative conductivity temperature gradient at the wall. And we have the negative sign for the heat flux in the definition, mainly because we are assuming the heat flows from a warm location to a colder place, right? And that is in the opposite direction of the temperature gradient. It's just a mathematical play here, right? Positive heat flux is in the direction of negative temperature gradient. Is there any questions so far? So these are the things we talked a little bit about in the previous lecture, and you have seen it in your previous classes. And in this chapter, we are only going to introduce these, right? The thermal boundary layer, the regular boundary layer, and the importance of them. In the next chapter, chapter 2 and 3 mainly, we are going to formulate these boundary layers. We will find the solutions on how to calculate the thermal boundary layer. We will see the formulas on how to calculate the thermal and the regular boundary layers thickness, and eventually the shear stress. And using that shear stress, we are going to calculate the drag. Okay. But let's talk a little bit about the effects of this boundary layer on aerodynamic forces, right? Okay. So before moving forward, I just want to mention a couple of principles. Let's say we have a couple of notes. Let's say we have a flat plate. We have flow approaching this flat plate, and we already know that a boundary layer will form. The boundary layer thickness is going to increase as we move on the flat plate from x equals to 0 to x equals to whatever, right? And at some point inside this boundary layer, there will be a transition to turbulence. Is there anyone who doesn't know what the turbulence flow is? Or let me change the question a little bit. Is there anyone who has never heard of turbulence? Okay, that's good. So let me ask you my next question. Who can tell me the difference between laminar flow and turbulent flow? Because this is another classification. Yes.
Laminar's like predictable and other molecules are
So laminar flow is orderly, right? It is ordered, right? All of the, as you mentioned, all of the streamlines are moving in a very good order. Everything is predictable, if you will. But when you get to the turbulent flow, this is where everything becomes unpredictable. You will see a lot of vortices, a lot of unpredictability, right? In general, when it comes to shear stress at the wall, the velocity gradient at the wall for a laminar flow is smaller than the velocity gradient at the wall for a turbulent flow. Okay, that's a general rule. So which essentially what it means is this. We're going to see this type of velocity patterns in a turbulent flow with a very huge gradient compared to the laminar flow. Sorry, this with a bigger gradient. The gradient is going to be bigger. So what does it mean for shear? We have, if we multiply everything by viscosity of the flow, the assumption is it doesn't change with this transition. So viscosity is going to stay the same. So the shear stress at the wall for a laminar flow, I'm going to call this L, is going to be smaller than the shear stress at the wall for a turbulent flow. Okay. So why is this important? Or let's actually talk about the importance of Reynolds number first, and then we'll move from there to the importance of the increasing shear stress. As you have seen in your heat transfer and fluid mechanics, Reynolds number is the number to go for when you want to determine when you want to determine whether your flow is laminar or turbulent, right? Flow over cylinder, you have a Reynolds number that tells you whether this flow is laminar or turbulent, or flow inside the pipe. Let's do inside the pipe first. We have a Reynolds number that, does anybody remember what is the transition to turbulence inside the pipe? That's all right. Don't need to know. We have a specific Reynolds number, which is a function of your rho infinity, V infinity, the diameter of this pipe divided by mu infinity, right? But on a flat plate, Reynolds number is a function of the length scale, the length of the pipe, which essentially tells you that at different locations of this flat plate, you are going to get different Reynolds numbers. So we are going to have two different Reynolds numbers when you're dealing with the pipe. One is going to be your with a plate. Your plate's total Reynolds number, let's call it plate total Reynolds number. And the other one is going to be a function of the distance from the leading edge of the flat plate. This one is called the local Reynolds number. And we already know that Reynolds number is important in this transition. And since we have this concept of local Reynolds number, which essentially means that without increasing the V infinity, without changing the gas or fluid, the Reynolds number will increase throughout the plate. And this is going to cause this transition from laminar to turbulence, okay? But this doesn't happen inside the pipe. The Reynolds number inside the pipe is not a function of the length of the pipe, it's a function of diameter. This tells you that going into the pipe, your flow is either laminar or turbulent. It's not going to change. But on a flat plate, it will change. It will start with laminar, then will move to the turbulence. And this is all inside the boundary layer. We are not talking about whatever that is happening outside of the boundary layer at this point. Okay. So we saw that the shear stress becomes bigger when we are essentially transitioning to turbulence. And in general, this is something that we actually have to remember as well. Reynolds number gives us a measure of inertial forces, inertial forces versus the viscous forces. So lower Reynolds number, lower Reynolds numbers are telling us the viscous forces are more dominant, which essentially means that your flow is going to be more orderly. When inertial forces become more dominant, your flow is going to become unorderly, turbulent. So we have all the basics. Let's see if we can answer this question. What is going to happen to the flow when we have a higher shear stress? Or what is going to happen to aerodynamic forces when we have a higher shear stress? It will increase the drag. So shear stress is, did you say? Yeah, I can't see your mouth moving, so I have to get. So higher shear stress is directly related to higher drag. And we have different types of drag. We have the two types that we are going to become familiar with today is the pressure drag and the friction drag. The shear stress is directly related to your friction drag. You essentially, if you recall, we had this friction coefficient that was your wall shear stress divided by Q infinity, right? Your wall shear force. So that's why we only have the division by the Q infinity. Okay, so your shear stress is very important in the determination of friction drag. So what does it mean? The idea is when you assume the flow is inviscid, so I don't have here anymore, we are assuming the shear stress is 0. So what is going to happen to the drag force when the shear stress is 0? The friction drag specifically is going to become 0. And this is something we have talked. You wanted to say something? Oh, 0. Okay. This is something we have talked about. I think, hopefully, we have talked about in the previous lectures. I have another class in which I talked about a similar concept. So I got, I'm not sure which class. In which class I've already talked about this, but I think we have already talked about the fact that when you remove the viscosity effects of friction from your analysis, you're going to lose the friction drag. That's the first thing. But there's other thing that's happening as well here that is going to affect your pressure drag. Let's see that. Okay, and this is also directly related to the body layers, the formation of body layers, but it is not directly related to the shear stress. It is also related to the shear stress, but not that direct. Okay. When you have the body layer, at some point, your pressure here is gonna become, at some point, it's gonna change its sign. So it's gonna become what's called an adverse pressure gradient. Your pressure gradient. Pressure itself is it's a scalar. So pressure gradient is the thing that is going to change the sign. So what does it mean? It means that the flow is going to be pushed near the vault, is going to be pushed in this direction, right? The air molecules or whatever are going to be pushed in this direction, right? The flow is moving in the other direction, in this direction. So we have some pressure that is pushing the flow in this direction, right? But at some point here, because of this shear stress that is present here, the flow, the pressure gradient is going to change its sign, which essentially means that the flow is going to be pushed in this direction. So after this, some of the flow will be moving in this direction. And the velocity distribution you're going to see inside the body layer at this point is going to look like this. Like this. So we are going to get some flow that is moving in the other direction. This phenomena, we are not going to go into the details, the details of physics of this as much, but the phenomena itself, I'm pretty sure you are, hopefully you are familiar with the phenomena. But is there anyone who can tell me what is this phenomena called? No, not vortex. But thank you for participation. That's important. Flow separation, exactly. So essentially, flow is going to separate from the plate or airfoil or wing or whatever you have. This flow separation and this adverse pressure gradient is actually there because of the viscous forces, because of the resistance of the wall to the flow that is going to be translated to the flow through the viscous forces, right? If we didn't include the viscous forces, we wouldn't have seen the flow separation. But in reality, this happens, and this is actually a very important phenomenon in aerodynamics. In aircraft aerodynamics, car aerodynamics, in any kind of aerodynamic analysis that you want to do. Okay, so viscous forces, important. That's the idea. And this is actually going to contribute to the form drag or drag by pressure, right? Two types of drag. Friction drag is there because of the friction. Pressure drag is also there because of the friction. So if we don't include the viscous analysis, what's going to happen to us is that we are going to lose any type of drag that we can calculate for this body. So the point being, viscous fluid flow analysis is very important in aerodynamics, but we can actually safely remove the viscous fluid flow analysis and get a very good idea about the lift. Why is that the case? It's because the body layer is so thin, is very thin. Okay, the normal pressure outside of the body layer and the normal pressure on the wall surface are essentially the same. Okay, and the lift generation is mainly, and we are going to talk about this in more detail later, is mainly a function of the pressure difference between the lower surface and the upper surface. Okay, so if the pressure, normal pressure outside of the body layer is essentially the same as the surface, for lift calculations, which is mainly a function of this pressure difference between the bottom and the top surface, we can just safely assume that the viscous, the boundary layer does not exist, and the implicit assumption is correct. And this is what people did until, because people didn't know about the presence of boundary layers, right? Until 1904. So we already had some analysis of flight. There were people who were making not planes, but devices that could fly. Like we had gliders. And this guy, a very important guy in fluid mechanics, Ludwig, I don't know, Ludwig Prandtl, was one of the first people who observed the boundary layers and formulated them. And understood, I mean, they understood that without the viscous analysis, they understood there is a problem because they couldn't calculate any drag, right? But they didn't know how to solve that problem. And Prandtl was the one who came up with a solution. Any questions? Yes.
You said that there's no pressure drag, like with the implicit assumption. What about the pressure on like the leading trailing edge, like that's not on the upper board?
That's yeah. That's a good question. So you have to go back to the direction of the pressure that is being applied, right? Let me answer your question this way. It is impossible to calculate the drag by pressure with the inviscid flow analysis. Does it make sense? Okay. So it all goes back to the type of analysis, right? And we're going to see that later on, actually, in chapter 2 and chapter 3, that the drag you calculate, not just that, because of the inviscid flow assumption, we will see a case that even the lift is going to be 0. And we're going to see that later. Well, it doesn't mean that if you do the analysis, you won't get a pressure difference between the leading edge and the trailing edge, but the analysis is so off the rails that doesn't really give you any meaningful results. Okay, so if there's no other questions, let's move on to, yeah, usually when I talk about boundary layers, I go. Someone has to stop me because this is my topic of research. Okay, so let's talk about a little bit about flow separation over different bodies and the values of that coefficient you want to expect. This is, I'm not gonna talk about this for a long time. Hopefully we'll just pass over them. Let's say we have this type of bodies, a flat plate that is placed perpendicular to the flow. And then we have a flow that is crossing a cylinder. Let's say we have an airfoil type thing, flow crossing over it. And let's say we have a small cylinder. The thickness of all of these are D, thickness that the flow sees. And all of them, we have the flow at the same Reynolds number, 10 to the power 5, except for the last one, which is an example of, yes, actually this one is also Reynolds number, 10 to the power 4. This is straight out of your book. So we talked about the effects of viscous flow. We talked about the adverse pressure gradients. You will get the biggest flow separation here. You will see a lot of wakes. The same thing is going to happen here, but the flow separation region is going to be smaller. And here, the airfoil is actually the most optimized form of a flying object, if you will. Then we have the flow separation around the cylinder. So the point here is, as you increase the velocity, you are going to dampen the flow separation. The flow is going to separate from your wing at the later stage. We don't want to go into the details of why that happens, but that usually what happens is with a turbulent flow, with a higher velocity flow, you're going to have a smaller or thinner boundary layer, right? You're essentially damping. When you increase the speed, you are decreasing the effects of the region that the boundary layer is dominant, right? But the values you're going to see for this type of analysis, for a thickness, a given thickness D, you're going to get this range of drag coefficient, 1.2. I just want to make you familiar with the ranges of, I'm sorry, this is 2.0. I just want to make you familiar with the ranges of drag coefficient you see. So you don't calculate a drag coefficient of 1,000, right? That usually doesn't happen, okay? For a cross flow over a cylinder, we have a smaller flow separation region, so we expect a smaller drag coefficient. For a flow over the airfoil, we get even a smaller drag coefficient. And here, for the last one, with a very higher velocity, as you would expect, we get a small drag coefficient because the flow separation region is the smallest. But what do you think the drag coefficient is here? And the diameter of this cylinder is 1/10 of this diameter. What do you think the flow separation, the drag coefficient is there? It's a smaller shape, right? Would you expect to see a smaller drag coefficient, a higher drag coefficient, or similar to the airfoil one or to the cylinder one or whatever? Higher. Why higher? Okay, just a guess. That's an acceptable answer. About the same as this one or that one? Okay. So what you're saying is that you would expect to see a drag coefficient of 1.2, right? The same as this. You are correct, actually. You will see the same, essentially the same drag coefficient as the bigger cylinder. We have a bigger area of flow separation compared to the airfoil, and we're gonna get a bigger drag coefficient. But we talked about the presence of two different drags, drag by pressure and viscous drag. I'm sorry, friction drag. Let's see what is the contribution of each type of drag to each type of these cases. Let's think about it. Which do you think will contribute more to the drag force in this case? Pressure drag or viscous drag? Viscous drag was directly calculated, no, friction drag, sorry, friction drag. Friction drag is directly calculated from the shear stress, right? It is a direct function of shear stress at the wall, right? Pressure drag is very highly proportional to the adverse pressure gradient, the flow separation in general, right? It's very highly proportional to that. So which one do you think is going to be dominant here?
The second one, the pressure.
Pressure drag, why?
Because it's not much length on the wall.
Exactly. So the length that is covered by the wall, the skin friction is going to be small. So the total friction drag is going to be smaller compared to this huge area of flow separation. the pressure difference between these two sides is very huge, right? So this flap is being pushed in the opposite direction of the flow with a very high force. What about this one compared to this? Let's say, I'm just giving numbers. Let's say we have, in case 1, we have 10% friction drag, 90%, and these are just ballpark numbers. These are not accurate numbers. What about this? What about this cross flow over the cylinder? Again, you have to compare the area that is being covered by the Barney layer for the shear stresses and all of these things, and the flow separation area. 50-50. It is usually actually, it really depends on your starting point of flow separation. If your flow starts separating from here, then you will essentially see the same contribution. If it starts from here, the contribution of the Barney layer is going to be higher, and so on and so on. But usually in lower speeds, the flow starts separating much, much earlier. What about the airfoil? In a perfect case, in the case I've drawn there, you see the flow separates much later, right? So we have this huge presence of Barney layers here on top, which means that we will have a very huge contribution of friction drag, okay? And then we will have a small contribution of the pressure drag. What about this one? This is essentially the same case as this one, right? You will get the biggest contribution from the pressure drag and the smallest one from the friction drag. Since it also has a very smaller diameter in general, the contribution of friction drag is going to be smaller anyways. And then you can do the same analysis for this one. So it is important to understand what type of phenomena is going to contribute to what type of drag. And we are actually going to learn how to calculate the pressure drag and the friction drag, both of them, later in the course. But we are mostly going to focus on lift calculations. Okay, any questions? What time is it? Okay, so that's it for chapter 1. There are some parts of chapter 1 that we didn't go over, like the importance of flaps, the lift coefficient versus alpha, angle of attack, Dirac coefficient versus angle, all of those things. But I will go over all of those in more detail later on. I think it's better for us to have a better understanding of lift coefficient, Dirac coefficient in general, to understand those figures and plots. So yeah, so we can go ahead and start the problems that we want to solve. As I said, I'm going to read the problem to you. I'm going to give you a couple of minutes to think about the solution. And then if there was a volunteer, you can come to the board. For every time you volunteer to come to the board, you'll get a bonus point. When you come to the board, you don't have to have a correct answer. Just have to be brave enough, I guess. That's the only requirement. We are going to solve this together. And the reason I give you this option is because I want you to be a little more engaged in class, I guess, like not to sleep, which happened to myself a lot. So I feel for you. Okay, let's do this. This is, you want to consider an infinitely thin flat plate of chord C. So a flat plate of chord C at an angle of attack alpha, alpha. That's a very big angle. In a supersonic flow, the pressure on the upper and lower surfaces are different, but constant over each surface. So we have uniform pressure distribution. Pressure on the upper surface, lower surface is going to be higher. So let's call that C2. And the C1. Okay. You want to calculate the location of center of pressure. X of Cp. Just think about it for a couple of minutes and we'll go over it. But in general, whenever you're asked to calculate the center of pressure, you have to calculate the moment over the leading edge, right? And then calculate the forces, the normal force, for example, in this case, or the actual force, whatever force that is creating that moment over the leading edge. And then you divide your force, you divide your moment by your force, right? The total forces. Let me try to help you this process. So we have an equation for the m prime of the leading edge, right? This is a two-dimensional flat plate, so we are going to use m prime. We want to find the location of center of pressure, right? We don't know that. The idea was at the center of pressure, all of the moments that is generated by pressures and shears, we don't have any shear in this case, so all of by pressures are going to cancel each other out. So we are going to have one force present, right? Which has two components, A prime and N prime. Sorry. This case, it is an infinitely thin plate. What does it mean? No, that is true. There is no skin friction, but it's because we said the shear is negligible. That's something I think I negligible. I forgot to mention. Okay. I saw a hand over there. No. What does an infinitely thin flat plate mean for our analysis? X is equal to dx. Not necessarily. So what does it mean in general? It is an infinitely thin plate. It means
the direction and the dimension in one direction is equal with respect to other directions.
Exactly. So it essentially means that the thickness is 0, right? It's just a line, right? Okay. What does that mean for the moment on the leading edge? You don't need to worry about the actual force, right? The actual force is not going to have any R, right? If it was an airfoil, you had some actual force here, right? That would generate some moment here. But since the thickness is 0, the actual force is in this direction, and this force does not create any moment. So you only need to calculate the normal force, N prime, okay? And you only need to calculate the m dot prime LE, m dot prime of the leading edge, and m prime, not m dot, m prime of the leading edge or the leading edge divided by n prime is going to give you x of CP. Okay. Do we have any volunteers? You want one? Okay, we have a volunteer here.
I need the equation.
I'm gonna give you the equations. Don't worry about it. We are gonna ask someone in the audience to give us the equations, right? There's something I also should mention to you guys, that there is an inconsistency in the m prime of LE calculation that she brought up. Actually, she came to my office. We talked about it, and there's an inconsistency there. There should be a negative sign in the equation, but we are going to use what your book has done, and we're going to use that equation in general. So m prime of LE. Can you tell her the equation, the most general form of the equation? Page 23, or can anyone? You don't need to draw all of those things. Just write down the equation. Okay. So it's the integral from 0 to C, or
Can I have the equation?
yeah, he's going to tell you the equation.
Mhm.
He's going to read it too.
U cosine theta plus tau u sine theta times x, the whole thing times x, and then minus pu sine theta minus tau u cosine theta, whole thing times y, dsu. And then
You have to close the bracket.
before the dsu.
Yeah, before that's it. Okay.
And then plus the lower edge, which is another integral from 0 to c, I think.
Yeah.
And then minus PL cosine theta plus tau L sine theta, whole thing times x.
Yeah.
And then plus PL sine theta plus tau L cosine theta, whole thing times y, DSL.
Okay, what is the first thing you can take out here in this equation? Tau, right? Because there is no shear. So just take out all of the taus. Okay, what else?
It's about theta because these are normal forces. So cosine theta is equal to 1.
Okay, so what she's telling us is that which is correct, is that since it's a two-dimensional case, the pressure and shear are in the same direction as the normal force and the actual force, right? There is no curvature. So theta is essentially 0, right? Cosine of theta, all of the cosines will become 1, all of the sines will become 0, right?
So what is theta defined as again?
Theta is the angle between, let's say this is your airfoil, this is your coordinate system, this will be your n, this will be your x, right? But your pressure will be normal to this surface, not this line, right? Theta is the angle between normal force and pressure at every point, right? And actual force and tau, yes. Here, not yet, right? The angle of attack comes into play when you want to relate lift and drag to the normal and actual force, right? And we're going to get there later, not in this problem. So that's, we have, what can we do about ds? What is ds here? Do you have any ideas?
We can just assume that because here we can assume this as c direction, and omit the x and y. So at last we will have p upper minus p lower
Okay.
equal to c1 minus c2.
C1 minus,
C2 here.
the values for pressure.
Yeah, the
So
value for
PU minus PL, that's what you're saying, is that PU minus PL times X, okay, that's
Yeah.
we cannot just remove X, right?
Yeah.
Times ds, okay? But the question I have is, what is this ds? ds is a small element of the surface, right? On which
Yeah,
this
it's
is
a
this
gradient
element
element.
here, right? It's a let's say this is a 3-dimensional with a unit depth. So your ds is going to be, ds is going to be dx multiplied by 1, right? So it is px dx. Does that make sense? P minus pu minus pl x dx. So
your ds is really just the dx.
dx in this case, but it's a flat plate with a unit depth, right? So it's an element of surface, element of a small element of area. This area of that small element is dx, which is this length here multiplied by your unit depth. Okay. So you forgot the x. There is an x here as well. Okay. So what is this integral? Pu minus pl is given. We know the value c2 minus c1, whatever that is. And what is the integral of x dx? Exactly, from 0 to c. So your f prime is going to be pu minus pl c squared over 2, right? Okay. What about n? Can you give her the formula for n prime, the normal force?
I have it here if no one else has it. It's negative integral from the leading edge to the tail edge,
Mm-hmm.
and then pu cosine theta
Uh-huh.
plus tau u sine theta.
Let's forget about the tau part, because we already know that they're gonna be canceled out.
Right. DSU, I guess is really dx.
So pu cosine of theta ds,
Yeah.
right? dsu, and
then plus another integral from leading edge to tail edge. PL cosine theta.
pl cosine theta. Okay. Theta was 0 degrees, cosine of theta is 1, right? So, and ds is just dx multiplied by 1, right? So you're going to get pl minus pu dx, which is x, right? From 0 to c, which means that it is just c. C, exactly. Okay. So we have the force, we have the m dot of LE. We should be able to calculate the center of pressure, right? Just plug that in. It is going to be pu minus pl c squared over 2 divided by c multiplied by pl minus pu, which I think we have missed a negative sign here. It should be pu minus pl, but that's all right. And eventually, you're going to get c over 2, right? Eventually. That's your center of pressure is at c over 2. Thank you. And since you're the first one who volunteered for this, you're going to get 2 bonus points. See, I just give out the bonus points for free. like Oprah, right? Everyone can get a bonus point. Why not? And so so a couple of points about this problem is that if you can maintain a uniform pressure distribution on top and the bottom, your center of pressure is always going to be independent of your pressure, okay? And independent of angle of attack, okay? The location of center of pressure. But this is something that doesn't really happen because it actually happens for flat plates, a small flat plate in which the effects of bonding layers are very small and the angle of attack itself is also very small, okay? But in reality, this really doesn't happen at all, except for the very, very small scope of cases. It has to be a flat. Okay, so let's move on to the next problem. Let's see which problem it was. Yes. Yeah, that equation here. You're right. Thank you. That's why we get the name. That was my mistake. Thank you. Yes.
One of them was that DS.
In this problem. Okay. So the assumptions, let's go over the assumptions. The first assumptions we made, this is the first assumption that was given to us in the problem, is that the shear is negligible, which essentially means that these shear stresses are zero. Okay. The second assumption we made was that this is an a very infinitely thin plate, right? And that infinitely thin is a mathematical definition. It essentially means that you can assume the thickness is zero. What's going to happen to us when the thickness is zero? This axial force is not going to have any arm when it comes to the leading edge. So it cannot create a moment, right? That's the second assumption. So in our calculation here, we didn't really need to include any other force other than the n prime. Which is the general case, okay? And what else? When it comes to ds is a small element of surface. We don't have any curvature here, right? It's just a regular plate. Your surface area is this distance multiplied by the depth, right? For a very small part of this, which is dx, the surface area, yes, is going to be dx multiplied by 1. Whenever it's not kept, not necessarily. It is actually, you shouldn't be afraid of this, right? ds is an element of surface. Okay, and we're going to come back to this mathematics in the beginning of chapter 2. But let's say this is an airfoil, and this is your wing, right? ds is going to be a small element of surface on this airfoil, right? It is going to be this length, whatever this length is. Let's call it very small, 0.001, right? A very small, multiplied by this, which we call a span of the wing, b. Okay, does it make sense? In our case, since it was a flat plate, this element was exactly the same as dx. Does this make sense? In our course, yes, because you usually deal with flat plates. Okay, but in general, or no, yes. Yes, yeah, definitely, sure. That's another way of going about it. Yeah, because it's essentially y is 0 here, right? Y doesn't change. Okay, if there's no other question, let's move on to the next problem, which is a Buckingham Pi theorem problem. Let me see which problem was that. So you had one of these problems in your homework, and the second one, this is actually something that I really want to go over in the class, because we are going to be introduced to another type of drag, which will be out of the scope of this course, but it's not a bad idea to know about it. So this is the text of the problem. The shock waves on a vehicle in a supersonic flight cause a component of drag called the wave drag, d of w. So that's a general definition. We are going to have an additional form of drag that is going to push the whatever object that is flying in the opposite direction of the flight, or in the direction of the flight, if you will. Okay, that is called the wave drag. And that only happens because of shock wave. It only happens in supersonic flight. Okay, and we can find the wave drag coefficient based on the general idea of force coefficient we had before. So the general idea of finding any forces coefficient was that force, let's call it the other, divided by dynamic pressure multiplied by your area, a span area, right? That was the idea. That was the general definition. We have gone over it. Hopefully you will remember this definition of the force coefficient by end of time. Where S is a suitable reference area for the body. In a supersonic flight, the flow is governed in part by thermodynamic properties, meaning that temperature becomes very important, right? And that flight itself is going to be a function of your heat capacity, constant pressure heat capacity, C of P, constant volume heat capacity, C of V, and also the ratio of the two. If you recall from your thermodynamics and fluid mechanics, or heat transfer, I guess, gamma, Cp divided by Cv, constant heat capacity at constant pressure, C of P, heat capacity at constant volume. You are familiar with these terms, right? You have seen this before, hopefully. And we want to use the Buckingham Pi theorem to show that CD, C of D, and W, the drag coefficient, the wave drag coefficient, is a function of Mach number and gamma, the ratio of the specific heats. So we are given the dimensionless parameters we have to find here, right? Okay. It should be CD using the Buckingham Pi theorem. It should be CD with the wave drag coefficient. It should be the Mach number. It should be the ratio of a specific heats. We are given those things. So this is good. And I'm going to give you some help and give you like a couple of minutes to think about it. I will probably solve this myself because we are running out of time, but we'll see. Okay. Sure.
Are these similar to questions we could expect on like an exam?
Yes.
These kind of questions.
So in general, if you want to know what kind of question you're going to get from chapter 1 in an exam, is you most probably will get a Buckingham Pi theorem question. You may get a question like the previous one we saw, right? I highly doubt that, but it is possible to get one of those questions as well, if you're concerned about an exam, which I guess you should be. Yeah? Okay. So let's see. The first thing we want to find is the dependence, the functionalities we have. the wave drag is a function of what? Is of course a function of all of those nice parameters we have seen: V infinity, density, what else? The speed of sound, and we were told that it is also a function of heat capacities, so Cp and Cv. Is there any other parameter that you can think of that you want to add here? Viscosity, let's say. Let's add viscosity. What else? dW is a drag force. That's you don't need to know any equation. That's the beauty of Buckingham Pi theorem, right? You don't need to know the real equation between all of these parameters. You just need to find the important parameters. You want to say something? Well, there is one thing that I'm missing, and it's very important actually here. Reynolds number is already a dimensionless parameter, right? So we are talking about the dependence of force on non-dimensionless parameters, because the goal in a Buckingham Pi theorem analysis is to find this dimensionless parameters, right? To remove the number of variables, to reduce the number of variables. Okay. We are missing the length scale. Yes. Yeah. Is that what you want to say? We are missing the length scale here. All right. So C, the chord length. Well, we don't want to use viscosity here because we are dealing with supersonic flights, and in supersonic flights, as I said, as you increase the speed, your boundary layers are going to be smaller and smaller and smaller. So the importance of viscosity becomes less and less. Right? It doesn't mean the flow is not a function of viscosity. It's just it is not as dominant, right? Whenever you're dealing with high-speed flight, high-speed anything, right? Think of the definition of Reynolds number. Reynolds number, inertial force divided by viscous force. So high-speed flight, higher inertial force, less dominant viscosity. Okay. Okay. Well, what are the fundamental units, fundamental dimensions that are present here? That's the next step, right? Fundamental dimensions. We have mass, right? It is present here. See, this is the chord length. In viscosity, it is present. Mass is present. What else? Which other fundamental dimension is present here? Time, right? In velocity, in many of them. So mass, time, and length. What else? Is there anything else that is present? Exactly. So temperature is also a fundamental parameter, and it's present here, and we're going to use degrees for it. So let's try MTL and degrees. Your book uses degrees for it. That's why I'm just following the book. Okay, so we have 4 fundamental parameters. We have, the ideal was we have to rewrite this equation as this function as we essentially have to bring dW to this side and get G of dW, V infinity, whatever, and C. Okay. So how many parameters, how many variables do we have here? 1, 2, 3, 4, 5, 6, 7. How many fundamental parameters we have? Fundamental dimensions we have 4. The number of dimensionless parameters we want to get is number of dimensionless parameters is 7 minus 4, 3. Okay, that was the beginning of Buckingham-Pai's theorem. Okay, so just choose one of the 3 that you want to take as important parameters. That was the idea. Let's choose velocity as pi1 for the pi1. So we're going to get v infinity to the power a. Velocity is going to be power 1. Rho infinity power a infinity power b, cp infinity, cp power c, multiplied, cv power d, and then c power e, and then velocity multiplied by velocity. This was the idea. You're gonna have 3-dimensional parameters. You take 3 of the parameters, you choose their power to be 1. For the rest of them, you just give them like A, B, C, Ds. These are the powers that we have to calculate. You may want to ask yourself, how can I be sure that this parameter that I'm choosing is the correct one? And again, we have talked about this before, but it doesn't really matter, right? Eventually, let's say you choose the incorrect parameter here, what you're going to get is the relationship is going to give you the correct dimensionless parameter, but the difference is going to be, like, let's say your dimensionless parameter is Reynolds number, you're going to get 1 over Reynolds number, right? So the powers are going to be the negative sign, right? If you choose the right, or you're going to get the square root of Reynolds number, right? So the point is, it doesn't really matter which of the 3 parameters you choose. It should give you the correct results anyway. So what is the dimensions for density? Is kilograms in SI, kilograms per cubic meters. It is mass M per cubic meters, length to the power 3 to the power A, multiplied by what is the dimensions of speed of sound? Speed of sound is very important here because we are dealing with supersonic flow, right? The Mach number is very important. Huh? What is the dimensions for speed of sound? Meters per second, that's the speed, right? In SI, so essentially length divided by T to the power B, multiplied by CP. What is the dimension for CP and CV? Does anyone remember? CP. It is in SI. Yes. Yeah. In SI, it is joules per kilogram Kelvin, right? And joules is Newton meters per kilogram Kelvin. What is newtons? It's kilogram meters per second square. So let's do this. Let's try to multiply. So CP, and you always, whenever you wanted to know the dimension of like heat capacity, you come to this general equation, Q equals to MC delta T, right? Delta T is Kelvin, M is kilograms, Q is joules, right? So C or CP has to be joules per kilogram Kelvin. Joules is Newton meters per kilogram Kelvin. Newton is still not a fundamental dimension, so it is going to be meters m mass multiplied by acceleration, so kilograms multiplied by meters per second squared divided by kilograms Kelvin, right? So these two will cancel out. You're going to get meters per second squared Kelvin. So CPCV, you're going to get M is mass, M is meter, sorry, length, divided by seconds squared, which is time squared multiplied by degrees to the power C. We're going to have the same thing for the power D. And then we have the V infinity multiplied by L divided by T. So we have, yes. Yeah, that's right. Sorry. So L square. That's good. Thank you. Thank you. Okay. So we have 4 unknowns, A, B, C, D. And we are going to have 4 equations. 1 for mass, 1 for length, 1 for time, and 1 for degrees. That's for pi 1, right? And since we are already out of time, I'm assuming you will be able to go from here. Is that a correct assumption or not? Yes, we have 1 yes. Your answer can be no. There's no. We can pick up later in the next. No. Okay. So we are going to pick up from here. Next lecture, we're going to finish this problem and then start working on chapter 2. If there's no question, that's it for today's class. And hopefully, if you're an online student, please let me know about the quality of the live stream. We went for 1 hour and a half. Okay. And yeah.